Hello, this is your homework on the support vector machine, and we haven't really talked about that in class, so I was going to make a video to help explain what's happening here. Um, so, so far we've been dealing with a lot of linear classifiers. So if you have linearly separable data, that's data that can be separated by a line. The A linear classifier finds the linear decision boundary. So we saw the perceptron do that. That's also what add a line does, and that's also kind of what logistic regression does if you threshold it. Logistic regression. I didn't mean to say linear regression. Logistic regression can find a decision boundary as well. Um, but the decision boundary isn't necessarily what this diagram is showing you as the maximum margin boundary. So let me go over here to the notebook and try to kind of explain that better. So let's suppose we have some data. I'll put some green points here. Once I figure out how this works, I'll switch to red, you bastard. So here's some red points. Here's some green points. And we want to come up with a linear classification boundary between those. So there are infinitely many. So like here's an example of a linear decision boundary. Here's an example of another linear decision boundary. So there's a special linear decision boundary that has what's called the maximum margin. So what the margin is if you make a perpendicular line from sort of every data point to the classification boundary, and then you look at the shortest one. So this would kind of be this one in this case. Then that makes something called the margin. So it's saying basically that you could fatten up this line that much and still have perfect linear classification. So there's kind of a bias which is implicit here, which is the maximum margin classifier will generalize better. That means that the intuition is if data starts to rain down according to nature's probability distribution on the data, that the maximum margin classifier will do better than an arbitrary linear classifier. And sometimes that's true and sometimes that's not. But this is the learning bias of the support vector machine, and in practice it works well. So what the support vector machine does is it finds a linear decision boundary, which is the maximum margin linear separator. So let's go back to the slides here, or the notebook that's kind of saying something similar. Yeah, so just like any other linear model, the support vector machine eventually finds what is this line? This line is just WTX equals 0. So in other words, W0 plus W1X1 plus plus WMXM is equal to 0. So this describes a hyperplane. In the data that we've drawn here, there's only 2 dimensions to the data. And so this would be a line like this would be W0 plus W1X1 plus W2X2 equals 0, where we have implicitly here an axis for X2 and an axis for X1. Okay. So now let's so remember what the hypothesis class is. The hypothesis is all the possible decision boundaries that the learning algorithm might output as an approximation to the target function. So what the slide deck is saying, I keep calling it that, but it's just the IPython notebook. So, you know, the things that it might output are just, sorry, I use so many different styluses, I get confused about how they work now, is the sign of WTX such that W is in R to the, we've been using M here for the dimensionality of the data. The Python is going to use D for that. I'm sorry about the disagreement. D kind of makes sense because D stands for dimensionality. So you guys know from watching the other videos that I put up recently that this just means a list of m+1 real numbers. And why is it +1? That's because of the bias. So remember we have, I should really be writing this vertically, but I'm writing it horizontally. So the vector x begins with 1, and then it has a first feature, a second feature, all the way up to the mth feature. Okay. And this is exactly the same hypothesis class that we used for Adeline and the perceptron. And it's also very similar to the hypothesis class for logistic regression. In fact, if you threshold logistic regression, you also get that hypothesis class. So now let's talk about the mathematics. Let me just make sure I'm staying synchronized with what's happening here. So there's now it's going to say something about the bias, just the usual mathematical presentation of the support vector machine. You know, we've been using the understanding that W is equal to W0, W1, W2, ... to Wm, and that X has a bias column built in, 1, X1, X2, ... to Xm. But it's often done, you know, instead of doing that, it's more typical that we say that the weight vector is just W1, W2, ... Wm, with this additional intercept term B, or this is kind of like the bias weight, which is just W0. They're just writing it at a different place, keeping track of it separately. And then X is understood to be just X1, X2, ... Xm. Okay, and what's the difference? So in green, with the way I've defined these things in green, if you write WT X, that's the same thing as in red. So the way I've defined those things in red, it would be WTX plus B. Okay, so do you see why? Hopefully, you know, you can just write this out, right? So it's W0 plus blah, blah, blah. We actually just did it on the previous page, right here. So the only difference is we're calling that W0 and it's happening automatically, or we're calling that B and we're adding it manually. That's the difference. So why do that? That's because when we start talking about the maximum margin separator, so let me draw some data here. I'll put in some red dots and I'll put in some green dots. Okay, and now let's just draw a cartoon of the maximum margin separator. It would be something like that. And here's the margin. Here's the margin over there. Okay. All right, so in order to start describing the constrained optimization problem that will result in the maximum margin boundary, we need to talk about sort of the mathematical formulation of what's going on with these margins. So the way we set up the math is you have to imagine that this is, we're looking at a two-dimensional plane from above, but what the decision boundary really is, this is just where a 3D plane is intersecting the x1, x2 plane. So I will try to help you visualize that, but it's going to be subject to my ability to draw. I think there's a better picture over here in the notebook. So here's a two-dimensional picture, similar to the one that we were just looking at. And here is a three-dimensional picture. So the understanding is, actually, could I just copy this? It seems possible, right? I don't know. We'll try this. Chances of success are low, but you never know. This is exactly the kind of thing stupid computers do well now. Yeah, that was I'd call that a failure. So what's happening is on the z-axis here, do you see 1? You see 1 on the z-axis here, and you see -1 down here on the z-axis. So what those margins are in terms of this picture is you make a stripe on this plane, this hyperplane here that's separating the data. You make a stripe on it at z equals 1, and you make another stripe on it at z equals -1. And now when you look at it from this overhead point of view, with one of those stripes, the one on the upper side, looks like this, and this is the stripe on the lower side. So we can write that down. So what would we say here? This is WTX plus B is equal to +1. This is WTX plus B is equal to -1. And this is WTX plus B is equal to 0. All right, and so notice that you can control these margins. You can make this margin move in, and you can make this margin move out by adjusting the slope of the plane. This is another thing that you have to kind of try to visualize here. So this plane is making a certain decision boundary where it intersects the light blue plane here. And it makes the same decision boundary no matter what its slope is. So I can make it steeper, or I can make it less steep. So I can, separate, I can make it this kind of like more parallel to the light blue plane, or I can make it more perpendicular to the light blue plane. So as I do that, the margins shrink and go out. So can you visualize that? So as I make that more steep, this margin shrinks down to here. This would be more steep. So same decision boundary, but the intersecting plane is steeper. Or I can do the opposite. I can make it less steep, so I can kind of relax this thing more, and then the margins would widen. So what we want to do is, you can imagine there's a certain decision boundary here. Initially this thing is kind of like perpendicular, and then you relax it as much as you can until the margins hit the data. So when the margins hit the data, then you've made it you've made the slope as shallow as it could possibly be, and then you found the maximum margin separator. So that assumes actually that the original decision boundary was the maximum margin decision boundary, so it's kind of circular there. So the question is, how do you find the maximum margin decision boundary? So this is where some math comes in. So let's just say we have a couple of axes here. Here's the x1 axis, here's the x2 axis, and we have a decision boundary. Okay. And this decision boundary is described by WTX plus B. And let me write out just explicitly what that would be in this case. So we're talking about W1 x1 plus W2 x2 plus B is equal to 0. All right, and now I haven't drawn it, but there's some z-axis coming out as well. And there's this plane coming up from here that we've been talking about, and I hope you can visualize that plane, because I need you to be able to mentally see it. I'm not going to be able to draw it. I want to be able to control the slope of that plane. So what is the slope of that plane? the slope of that plane is if I take a point here, let's say I just take a point on the line initially, and I look at the gradient of the function z equals wt x plus b. I want to look at the gradient of that where x are the variables. So this is a little bit different than what we've been doing. So if I look at the gradient of this with respect to x, let's come back to this picture here. We've got a little point anywhere. We want to know what the gradient is. That's the slope of this surface. That's well, it's the direction of maximum increase for this surface, and then sort of the magnitude of the gradient is its steepness. Because this is such a simple shape, it's a plane, it actually doesn't matter which point you sample from the light blue plane. The gradient at every single point is going to be exactly the same because the direction of steepest increase is fixed because this checkered thing is a plane, and also the magnitude of the gradient is fixed because the steepness is the same everywhere because it's just a plane. It's very simple. So it actually doesn't matter which point we sample the gradient at, because it's actually just going to be a constant. And what will it be? So here, this is the expression for the plane. So this will be dz dx1 dz dx2. And what will that be? So here's what z is down here. So if you take the derivative with x1 being the variable, then you get w1. And if you take the derivative with x2 being the variable, then you get w2. Okay, so if I look at sort of w1, w2 here, what you'll find, first of all, note that it's constant. It's completely independent of x1 and x2. It doesn't, like we said before, it doesn't matter where you sample that. If you take a point here, w1, w2 is going to point exactly perpendicularly. So this is the vector, w1, w2, and it points in a direction that is perpendicular to the decision boundary, and its magnitude, so the magnitude of w, where I understand this to be, the magnitude of the vector w1, w2, sorry for the inconsistent notation, which is the square root of w1 squared plus w2 squared. What that is the length of this line, and it reflects the steepness of the plane that's making the decision boundary. So in other words, it controls the margin. Okay, it controls the margin, because we said that there was a connection between the steepness of the intersecting plane and the width of the margin. So if the magnitude of the weight vector is small, then that means it's less steep, which means, I should write this down. So if this is small, then what happens? Then the cut of the intersecting plane is shallow, it's not very steep, and the margin is wide. On the other hand, if this quantity is large, then the intersecting plane is steep, and then the margin is small, or thin, or narrow. Okay. All right. So once you've now we've got actually the objective function of the optimization problem that we're going to set up to train the support vector machine. So what we want to do is we want to minimize this. We want to minimize the magnitude of w. Okay, so that's very easy. You can just have like a length 0 vector. So the solution to that is just w1 equals w2 equals 0. we have to minimize that subject to certain constraints. The reason you can't just do that is because then the margin would be infinitely wide. But we know that the margin actually can't be infinitely wide because it's subject to these constraints. It's going to run into these points. So we want to minimize that quantity. Turns out to be more mathematically convenient to minimize its square. So this is just w1 squared plus w2 squared. You want to minimize that quantity. Notice that this is a quadratic function of w equals w1 comma w2. That means that everything that shows up there is a product of at most two variables. So this is a product of w1 in itself, it's a product of w2 in itself. Okay, and so what are the constraints? We want subject to the constraints. So what are the constraints? So we need wtx plus b. So what is that? That's going to be like the height on the z-axis to be less than or equal to 1 if y is equal to positive 1. So the corresponding label is equal to positive 1. So to come back here, that's saying that that you can't have this margin go on the other side of these green points because that would violate that condition. So what that condition that I just wrote is doing is forcing the margin to be on the right side of the positive instances. And I'll do something similar here for the negative instances. I will say that wtx plus b is greater than or equal to minus 1 if, am I doing this exactly wrong? I think I'm doing it exactly wrong. This should be greater than or equal to 1 if it's a positive instance, because here's the corresponding input. So yeah, that's right. And now this needs to be less than or equal to minus 1 if y is equal to negative 1. So for the negatively labeled ones, this needs to be true. And for the positively labeled ones, that needs to be true. So notice that if we multiply both sides of this equation by y, no matter whether y is plus 1 or negative 1, we get this expression. So both of these expressions become expressible just in the single requirement that y times wtx plus b is greater than or equal to 1. So that captures both of those inequalities at the same time. So just check it case by case. So if y is equal to plus 1, then you multiply both sides by plus 1 and everything stays the same. It's good. If y is equal to minus 1, then you multiply both sides of this inequality by minus 1. So that makes a positive 1 on the right. And it also flips the direction of the inequality. So either way, you get this. So this gives you a family of constraints. Okay, so let's look again at the optimization problem that we're looking at. So we want to minimize w squared. So remember that this is just w1 squared plus w2 squared plus wm squared. We want to minimize that subject to, and now there's going to be one constraint for every data point. So it'll be subject to yi, it's supposed to be an I, wt xi plus b is greater than or equal to 1. So this is a linear, notice that this is a linear constraint for every I. For I equals 1 to ... up to n. And in the Python notebook, it's capital N. Sorry about that disagreement with the notation. So that's the translation. All right, so that makes sense, right? And then intuitively, what are we doing here? So we have some, let's just take a look at this optimization problem. This might give you some insight about what's happening. Now I'm drawing W1 and W2. So here's some quadratic function of W1 and W2 expressed as a topographical plot. And now we're introducing a system of linear constraints. So that means that we're constraining the solution. You know, so the absolute optimum maybe is right here, but when you constrain to these, when you restrict to these constraints, you have like this would be the optimum. So this is kind of the constrained optimum where you have to respect these linear conditions. Basically, the only solution that you can entertain has to be on the right side of all of these inequalities. So these inequalities are giving that kind of rectilinear region here, or this linear polygon. And the objective function is this quadratic function. So we're trying to find the optimal point, or sort of the, you know, the lowest point on this surface, subject to the constraint that the only solutions we can consider are inside this system of linear inequalities. Okay, so that turns out to be a certain kind of problem. Like you might be aware of linear programming is a way to solve linear constraints. This one is a little bit different. This is called a quadratic programming problem. Here's another picture of it. And so several of these are built into Python. The one that I settled on a long time ago to use is called quadprog. There's nothing particularly good about quadprog. So look here, they're defining what a quadratic programming problem is. And so this looks a little bit different than what I wrote before. So I'm going to go back to the slides and try to make sense of this and see how what we just did fits into this paradigm. So here they write W bar G W bar plus, is it A times W? Yeah, AT times W. Okay, so this is sort of a general quadratic function in the variables W. Okay, so I imagine that might not make a lot of sense to you. So let's do a concrete example. Let's say W is equal to, let's make it kind of interesting, W1, W2, and W3. So we're talking about three-dimensional here. Let's say that G is equal to 2, 1, 0, 1, 0, 3, 3, 1, 0. Actually, is that linearly independent? Yes. Okay, so now what happens if I do, make sure I got this right. I think I might have made a dimensionality. Yes, right. So this should be the transpose, and there's a factor of 1/2 here. All right, so let's look at what we get. What I'm going to do is I'm going to see what this is, and you're just going to build intuition about what about how this relates to a quadratic function of W. So let's do it piece by piece. So first, let's compute G times W. So what would that be? GW is equal to a very expensive and moderately good school near Washington, D.C. Ha, 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 ha. So this would be 2W1 plus W2. And we're going to be making a vector here. Okay, and now we do W1 plus 3W3. If you don't understand what I'm doing is matrix multiplication. And if you don't know what matrix multiplication is, you need to go back to school. I'm messing this up. So you have 3 times W1 plus, yeah, okay, sorry, I'm kind of slow, plus W2, just want to make sure I get it right. Okay, great. And now I do WT times GW, and it's associative. And so what is the result going to be there? This is going to be equal to 2W1 squared plus, actually, this is not going to be a vector, it's going to be a scalar. Scroll down and write the answer right here. So this is going to be equal to 2W1 squared plus W2 W1 plus W2 W1 plus 3 W3 W2 plus 3 W1 W3 plus W2 W3. And now let's collect like terms. Let's see, we have 2W1 squared, W2 times W1, we have 2 of those, plus W2 W3, we have 4 of those, plus 3 W1 W3. Okay, so notice every term here is quadratic. Every term is the product of 2 of the original variables. So there's this linear part that we haven't included yet. And the linear part is the reason that A times W is there. Let's make up something concrete for A to be. So maybe A is equal to 1, 0, 2. Just make up something generic like that. So what that's going to do is it's going to give us the constant part. Okay. Or not the constant part, the degree 1 part. So now if I add in this part ATW, what is ATW? ATW is W1 plus 2 W3. So for the whole thing, I can just tack that onto the end. So let me express things properly. So we have 1/2 times WTG W plus AT W. Okay, and what did that turn out to be? That turned out to be W1 squared plus W2 W1 plus 2 W3 W2 plus 3/2 W1 W3 plus, now it's time for this part, W1 plus 2 W3. Okay, and what we have is just a quadratic in, this is a quadratic in W. And there are many other quadratics in W, but no matter which quadratic you choose, ignoring the constant term, all of them can be expressed in this form. So that's why this is called the general quadratic in W. So all of them can be expressed that way. Well, let's come back and look at the second constraint, which is a linear constraint. A times W is greater than or equal to V. So A times W is greater than or equal to V. So let's make this concrete as well. Let's say that W is equal to the same thing as before. What did we say that it was? W1, W2, W3. W1, W2, W3. And let's say A is equal to 1, 2, 0, 0, 1, 2, 1, 1, 1. Okay, and let's say V is equal to 1, 3, 0. Okay. Now, what kind of, what would we get here? We would get a system of linear inequalities. The first inequality would be W1 plus 2W2 is greater than or equal to 1. The next one would be W2 plus 2W3 is greater than or equal to 3. The last one would be W1 plus W2 plus W3 is greater than or equal to 0. So this is just a compact way of expressing a system of linear inequalities. So you might be wondering, okay, but what is G and what is A and what is V and what is A? If I said that correctly. So in other words, I just made up these things. I made up A, I made up V, I made up G, and I made up A, and you're like, Professor Johnson, you're just making crap up. But what these are have to do with the optimization problem you're asking. So you're allowed to specify those to be anything you want. Like, and what are you going to be doing? Well, you have the quadratic that you want to minimize. You want to minimize that, right? And you have the linear constraints as well. So these numbers are, the values of those are going to be, this is why we call it a programming problem, because you just have to pick G and A to put everything in this form. That's very easy, right? G is just, it's very similar to the identity matrix, depending on how you represent your W. Yeah, so I'll suss all that out in just a second. And over here, obviously V is going to be nothing but ones, and then A is going to be cooked up so that you get this. Okay, so we've got it. And so here, now we've written out, let's just come back to this concrete example. So we did write out a certain quadratic. We did write out a certain quadratic function of W. You can see it there. And we did write out a certain system of inequalities. Now, if we were to put this into quadprog or any other quadratic programming solver, there actually is a solution. There is an optimum. And that's what quadprog does, is it finds the values of the vector W that actually optimizes this subject to these constraints. So what that means is, because our optimization problem that we want to satisfy to find the maximum margin boundary is a quadratic programming problem, quadprog can train the support vector machine. And so that's what all that's saying. And now this is trying to make sense of everything. So here I'm using this notation. If you read this notebook, you'll see instead of writing B, what I did is I used slightly different notation here. So what this means is everything in W except for the bias weight. This is everything in W except for the bias weight. So if now here the understanding is that W does include the bias weight. And in that case, you can just make G equal to the identity matrix. So what does that give you? That gives you all of the squares. All right. So here let's go do a concrete version of what I am saying right here. So come back over to the notes. Now let's look at a generic situation. Let's just say we have W, as I've been explaining it here, we had W is equal to W1, W2, W3, and we had this bias weight, which is W0. So what the notes are saying is that if you just have one big long W, so here I'll change the color because we're using slightly different convention now. So just imagine that this is W0, W1, W2, W3. So now I'm using the convention that the bias weight is built in. Now look at what happens if you do 1/2 WT, now let me call this I star. This is times W. Okay, and let's examine this. And what am I calling I star here? What I mean is it would be the identity matrix suitable for multiplication with W. But I am deleting the 0, 0 entry and replacing it with 0. So when you do that, what you get is 1/2 times W1 squared plus W2 squared plus W3 squared. So in other words, this is in green. This is 1/2 W squared, where this is the green W, which is ignoring the bias part. And this is I didn't put the 1/2 there, but we want to minimize that. Okay, so that's what we want to minimize. We want to minimize this. Okay, and we just figured out how to put that into the quadratic programming. Also, A is just all zeros because we don't need any linear terms at all. So in this case, A would just be all zeros. And now what I've done is I've created the quadratic programming problem, the objective function that we need for the support vector machine. And now the question is, how do you put in the constraints? So let's see how we would put in the constraints. So what we would do is, let's come over here. Let's make A equal to, in this concrete situation, let's look at these constraints. So the constraints look like this, okay? So if the bias is built into W, then this is just the same thing as W times WT X, if the bias is built in. If the bias is built into X and W, then that's what we're saying there is greater than or equal to 1. Okay, so now let's come back down and look at this mission. So here we're working in red, so we're going to assume that the bias is there. So we'll do, this will be Y1 plus, oh sorry, it's not plus, it's comma. Y1 X1, actually X1 1. Y1 is going to be kind of a lot of writing here. X2 1, Y1. Oh my god, I hope there's not a lot of data because I'm going to be tired of writing these rows. X3 1. Okay, but now these x's would be the particular data that you actually have. So, you know, your first data point will actually be some real numbers, and y will actually be plus or minus 1. So you're going to be filling this in with actual numbers, you know, not manually, but in a program. Let's just add one more row of data just so you can kind of see what's going on here. So suppose there's 2 data points. Here's the other data point. Y2, X1, 2, Y2, X2, 2, and Y2, X3, 2. Okay, so presumably there's a lot more data, but I'm tired of writing, and we'll just assume that there are 2 data points. So we're going to be multiplying this times W. So here's what W is. W0, W1, W2, W3. Okay, so what happens when you multiply, when you do matrix multiplication of A times W there? So this is A times W. Then that turns out to be Y1, WTX1 is the first entry. So A times W is equal to, and this will be Y2 WTX2. Okay, fantastic. And now we just want to set up an inequality, and what should we put over here? This is going to be our V. Obviously, it should just be 1 and 1. All right? So we load up this A with these entries that are actually determined by the data. So the A is basically the data. And then this V is just basically ones. And that's it. So now we've seen how to specify the quadratic programming problem to solve the particular problem that we want to solve for the support vector machine to find the maximum margin classification boundary. Great. And so now this just describes the documentation for the quadprog library. Of course, it would be wonderful if quadprog just by default used exactly the same notation that we use, but unfortunately it does not. It uses x as the variables. So it's saying x here where we would say w. So that's a little bit different. And where we would say the matrix A, it says the matrix C transpose. And where we say the vector V, it says the vector B. Okay, and then it also has other notations for, here we would say this was in the, it's D by D for the dimensionality of the data. Actually, it's D plus 1 by D plus 1. And you can read that more closely if you want to. So here is the first exercise I've actually done for you, just to show you how things work. So it says below, use quadprog to find the maximum margin W for the blob data loaded above. The solver will not like it if a row or column of G is all zeros. So what this is doing is it's taking whatever G you construct and it's sprinkling a little bit of numerical dust. So see how this is the identity matrix, and it's throwing in, it's multiplying each one of the ones in the identity matrix by 1/1,000,000th, and it's just to stop numerical problems from happening if the matrix is like linearly dependent or something like that. Okay. All right. And the solver really likes for G to be positive definite, meaning that this is true for all. I mean, this is true no matter what W is. So this ensures that G is positive definite. Okay, and so here's the solution. So we get the dimensionality of the data. G is initially the identity matrix of the right dimension, but I'm basically setting the upper left one to 0. So this is what I called I star in the notes over here. Sorry for all the translating, but what I star there is this theoretical thing. Over here in the actual code is what they're calling G. And A is going to be all zeros. Why is that? That's because A is all zeros, like we discussed before. And now this A is kind of tricky. So it's going to be basically Y times X is essentially what this is. And so when you get Y times X, it's going to be this matrix A. Because there's a scalar y here that you could just factor out on the left actually it's a vector. It would be like a broadcast operation, which we haven't talked about too much. But for every row, you can sort of factor out the scalar y. I think you can see that. And then we multiply times the X matrix. Now, for whatever reason, the quadprog solver, because of some quirk of its own, it prefers to take the transpose. And now V is going to be all ones. Why is V all ones? V is all ones for the reason that we talked about here, because this is the inequality that has to be satisfied. So now you can put it all into the solver, and this actually does find the optimal W. And then this just makes a plot. So this is not just a made up decision boundary here. What this is doing is it's actually plotting the real solution that was found by the optimizer for the blob data. And you can see that the margins are in exactly the right places. This is what plots the margins. And you'll just have to, I forgot, I did that years ago. But look, it's perfect. Okay. So this just takes a second to define what the support vectors are. So what happens when you do this is the margin touches one of the positive examples, and it touches one or more, if they happen to be collinear by some weird freak, of the orange ones here. And then it happens that that small number of finite points actually determines the maximum margin classifier. So if you threw away every single point except for those that touch the margins, those are called the support vectors, and then ran this problem again, you would get exactly the same solution. So that's a kind of information compression in a way. It's saying that as far as classification is concerned, all of the information about what's happening here with the SVM is contained in those 2 or 3 points. And in higher dimensions, it'll be more than 2 or 3, but it'll still be a very small number. And here this actually explicitly finds the support vectors for the particular data set. So here's a support vector. What this is w.x. So we're looking for that to be exactly on the positive margin. So that's approximately 1. So here's one of the support vectors on the positive side. And then on the negative side, there's this one. And there's this one is also evidently 1 because they are pretty close to collinear there just by some weird coincidence. And it's like a numerical question whether you want to consider this even being 1, you know, it's a little bit fuzzy. All right, and so I've not prepared my remarks very much after this point, but let's just keep going through here. Here's a 3-dimensional view of the same decision boundary. Try to use it to understand why WTX equals plus or minus 1. This is with the bias built in, gives different margins depending on W. There it is. We've already seen this picture before. You have to understand how this picture relates to the margins, or you're never really going to understand what's happening. Okay, so now it starts talking about soft margin, but we've been talking for a long time now. So I think I will stop this video and maybe we'll make another video about soft margin.